Thank you. So you see two people in bold on this slide. So usually it should have been Jan and me, but he got sick, so I'm presenting alone. And let's start. And we start, in our case, in a cloud environment. And we have some vulnerable binary that we want to execute. And we have an attacker. And the question for this talk is, how can we protect our code against ciphertext side channels? And our answer that we'll see during the talk is we'll get a hardened binary out of that and a sad attacker with our Cipherfix framework. So this talk was planned to be an attacker and a victim that are interacting and always discussing. And I won't do that now because I'm alone and I'm not an actress. So I'll just explain what attackers will do in some scenarios. Yeah, so let's start. We all sometimes have some code that we want to execute, and we don't always have expensive hardware to do stuff. So what do? We just rent someone else's hardware and execute our code in the cloud. But if we just do it as is, we don't have any protection. So if there's an attacker also on the same system, like the cloud provider, the hypervisor, then they can just read all the data in clear because we didn't add any protection level on top of that. So to conquer that, we can use a trusted execution environment, which gives us encrypted code and data so that the attacker now doesn't see all the texts, like the clear texts, but ciphertexts of that. And I mean, now we started thinking about making things secure, so we will also use constant time code. So the trusted execution environment still has side channel leakage, so we use code that is protected against timing side channels. So this means that we will always execute the same instructions. We don't have any secret dependent memory accesses or secret dependent branches in that. So at this point, it should work like charm, but still the attacker can do something with these ciphertexts. And I brought an example of a constant time implementation of a constant time C-swap. And what you see here is it's, for example, used in EDDSA, so in standard implementations that are used everywhere. What you see here is we have two buffers, like the X and Y, and we put them to the memory addresses. So these blocks are the memory addresses, and the colors and stripes are the ciphertexts that you see. And now we have some secret decision bit B, so we have two possibilities. B can be 0 or B can be 1. And if our bit is 0, then we don't swap these two values, whereas if the bit is 1, then we swap the values. And generally, this memory encryption from the trusted execution environment should protect our secret. So we don't see the value X and the value Y, but we just see the ciphertext of both of them. However, this memory encryption for whole virtual machine TEs is deterministic. So this means that if we write some value to any address, to different addresses, we will get a different ciphertext because of a little tweak value that is added. But if we now write the same value to the same address again, then we will see that, and that's what you see on the left-hand side of the picture. You write the same value again, so you see the same ciphertext. But if the bit B was 1, then you swap the values, so you wrote a different value to memory, and then you'll get a different ciphertext. And you can, by observing the changes in the ciphertext, you can leak the secret bit B in this implementation. So the first thought is it's a trusted execution environment, it's hardware, so maybe there will be a hardware fix, but there won't because it's too much overhead to add. So we have to do something in software, and that's what I'm presenting now. So the general idea is if this change of ciphertexts leaks information because it's dependent on the secret, then we just always change. So we add a random mask to every memory write. So you do not see the pattern of the previous slide anymore, but you always see a different ciphertext. So we do not touch the values, we keep X and Y as is, but we add a mask before writing to memory so that we change the ciphertext. And because the ciphertext now always changes, you won't leak the secret bit B. But if you do that for every memory write, you will have a very high overhead because, yeah, adding extra stuff to every memory write, that won't work. But we still start with our vulnerable binary and want to get a hardened binary out of that. So what we do now is some pre-processing to make the approach a bit smarter. And in our implementations, we do not have to protect everything. We have some secrets, but we also have many public values. So what we do first is we track the secrets. For example, you mark a private key, you track where it's going throughout the execution, and then you get a list of all memory accesses where some secrets were involved. So some potentially vulnerable accesses. And then you can add the mitigation to only these accesses that you got out of your pre-processing, out of your analysis step. And we do this by dynamic taint tracking in the first place, and then statically rewriting the binary so that you can just execute it on your system and have the vulnerable memory accesses masked. So the question now is, can an attacker still do something? I mean, how do we add these masks? You just saw an XOR on the slide, but that's not how it will work when you implement it. So our first thought was doing a fast version of that, and you have the plain texts on top, and we just add a mask buffer for every piece of data that we need to protect. And then we fill random masks into this mask buffer, and if you then add your plain text and the mask buffer together, you will get some data that you can write to memory. And this data then gets a ciphertext because of the trusted execution environment. But there are cases that are always public. These are easy cases. And there are cases that are always secret, like an instruction that only touches secret data. That's also easy. Then you can always do the mask additions that way. But there might be, for example, functions like a multiplication that is used for private data and for public data as well. And then you need to determine at runtime whether this function needs the public path or the secret path. Because if you came from a public path, no instruction will know about any masks, so things would just break. So you need to encode that somehow. And in this fast version, the way to encode that is have 0 as a mask for public data. Because if you XOR anything with 0, you will get your anything back. But yeah, for the secret data, we can just put random values in it. Well, not really random, because we have to exclude the 0. So what happens if we would sample random 0? Then we would have to resample, because otherwise our secret data would be treated as public data, and that's definitely not what we want. And this is something that could lead to an attack via like statistical measures. So we have to do something better in that place. So what we can do is we decouple this public secret information thing from the mask and add another buffer. This of course means some memory overhead, but it's okay-ish. And now we put the secrecy information in the secrecy buffer, like 0 for public values and 1 for secret values. And then we can end the secrecy buffer together with the mask, and then the mask will cancel out for the public cases, but will remain for the private cases. Now, next question would be, where does this randomness thing come from? The first approach would be to use RDRAND. I mean, it's cryptographically secure randomness, hardware support, nice thing, but it's really slow. It adds a factor of 20 in most cases. But the thing here is we are still in the trusted execution environment. So we are still in the encrypted scenario and so on. So we don't actually need the cryptographically secure randomness here. So we could also do something faster again. For example, the XOR Shift 128+ generator. It's also well studied. And the attacker in that case would also have a hard time to find a mask collision to be able to break the system. And we even came up with something faster because there are many cases without repeating writes. So you could just do even faster things with a custom randomness generator, like based on AES and I. You seeded, then you run one round of AES, and afterwards you'll have something new as your mask that you can put in your random buffer. And as soon as you reseed that from time to time with RDRAND, for example, for most implementations, it'll be enough. So this gives some trade-off. If you definitely need more security, you should stick to the slower versions, but there are also possibilities to make it faster. So let me quickly recap. We started with a vulnerable binary that is susceptible to the ciphertext side channels that you see. And if you add Cipherfix with an analysis to track all the secrets throughout the program and then rewrite the memory accesses that would otherwise potentially leak your private data, then you will get a hardened version of the binary with a sad attacker and protected data. We also have our code available, so if you have any questions, you can always reach out to us, and the GitHub thing includes a link to the paper as well, and some documentation, pre-configured images, and all that stuff. So, thank you very much for listening.